Good afternoon, everyone. Welcome to our final lecture of this Lincoln Math and Physics Week, which is very special as it is also combined with a Lincoln Physics Challenge Award ceremony. And the program of event is the following. I will first give a short introduction about hosting school university, as we do for every lecture and also for every award ceremony. After that, there will be brief award ceremony telling who are the winners of this year Physics Challenge, which will be then followed by the physics lecture about vacuum, given by the chair of Lincoln Physics Challenge and Lincoln senior lecturer, Dr. Fabien Paillusson. During the event, you can ask questions in varieties of channels. We have this afternoon with us winners of Lincoln Physics Challenge. They will be able to ask directly in the audience, and members of public can put questions in a live chat of YouTube or in a Padlet link, which will appear as well in a live chat, in case they would like to ask question anonymously. And now I go to the first part. I'll tell a few words about our hosting school, which also organizes a Lincoln Physics Challenge and Lincoln also Math Challenge as well, that we can just let me share my screen. And the slides went a little bit too fast. Just a second. Welcome everyone to our Lincoln Physics Challenge Award ceremony and to our final lecture of Lincoln Math and Physics Week. I'm Professor Andres Velendowski, Head of School of Mathematics and Physics, which organizes this event. Traditionally, you would come to our lovely campus in near the center of city of Lincoln, 10 minutes walk from the center, by the Brayford Pool, which was already port in Roman times. Nowadays, Lincoln is a small city of approximately 100,000 inhabitants. You visit us now virtually using this presentation, and we do hope that one day you actually will come to the city and look how nice we are. We modern university in a quite old city. City founded by Romans shortly after they came to British Isles. It was base of a famous legion number 9, Hispania, before legionnaires moved to York, so Lincoln was before York, and it received very prestigious status of a Roman colonia. and was a Lindum Colonia in times of Emperor Domitian. And you can see how kind of we think a city looked like. However, we do still have some Roman remains, and you can walk under the surviving Roman arch, or you can drive under it. And in fact, it's the only Roman arch under which the traffic still allowed in Britain. Next big step in development of Lincoln was in Middle Ages, when another visitors came to Britain, William the Conqueror, William I, soon after taking the power, were ordered to build a castle where Romans already spotted as a good spot on the top of Lincoln Hill. And opposite to the castle, he also asked to be built even more famous cathedral, Lincoln Cathedral, which some consider perhaps the most beautiful cathedral in British Isles, and probably one of the most beautiful in the world. At least it was highest building in the world for about 200 years, then wooden spire was on the top of it. As cathedral, it of course had a library. It's a medieval library. And if you visit it, you also might find an interesting note that one book actually was borrowed centuries ago to University of Cambridge, and it still did not come back. So I wonder what library fines will be for that borrowing. As a cathedral and a library, it was seat of learning for Middle Ages. There are various names associated with that, and one name is Robert Grosseteste, who was Bishop of Lincoln. He was teaching in Oxford University while working as a Bishop of Lincoln. And some consider that he was perhaps the first English scientist, or to be more precise, the first English physicist. And if we jump over the centuries, we then come to end of 20th century. Then actually university was open. Before was no university in Lincoln. It was open on this waterfront, which you've seen an image before at night, and at day it looks as glorious. It was opened by Her Majesty the Queen in 1996. Already in 21st century, College of Science was open, including School of Maths and Physics, which opened doors in 2014. And we hosted in this quite nice building named after Isaac Newton, another person from Lincolnshire. And next month, this building will be just 4 years old. It's shared together with schools of engineering and computer science. As a School of Math and Physics, so I'll also mention what degrees we offer. As people who listen us on YouTube, they might think, and also in audios, they might think about further studies. In physics, as the lecture is in physics, and event is Lincoln Physics Challenge Awards. We offer bachelor and integrated master in physics. We also offer bachelor and integrated masters in physics combined with philosophy, where philosophy is a minor part. So two quite old disciplines together. And we have also bachelor and integrated master joint award, mathematics and physics, so-called 50-50, and which is for those who incline towards, for instance, theoretical physics. And again, I mentioned this is our last afternoon for Lincoln Math and Physics Week as well. So welcome everyone. Now we will be moving to our next short part, presenting our winners of Lincoln Physics Award. So I'll just share another file, which in fact I did share before. Right, welcome to the award ceremony of Lincoln Physics Challenge. It is my pleasure to present the winners of this year competition, and first we will announce those who received commendation for their work presented to the committee. So the first, there are several commendations. Competition was quite strong for several nominations. There is more than one awardee in commendations. The first commendation is to Seth Tipping from Hills Road Sixth Form College, Cambridge. Congratulations, Seth. The next commendation goes to Santiago S. from the Priory LSST here in Lincoln. Congratulations, Santiago.
Thank you.
Next is Thomas Mitchell, who also receives commendation, and he comes from Loughborough Grammar School. Congratulations, Thomas. Our next commendation goes to Alexander Kessen Holland from Andelham School in Bodenham Wood. Congratulations, Alexander. And now we move to a next awards, which is a third place in Lincoln Physics Challenge 2020-2021. The third place is awarded to Raphael Davison. Congratulations, Raphael, who comes from King's College London Mathematics School. Next is a second place winner, and that winner this afternoon is Makafu Avivor from King's Edward VI Grammar School in Louth. Congratulations, Makafu. And now we go to the first place winners. And I just mentioned again that competition was very tough, and we could not determine a single winner. Therefore, the first place is shared, equally shared between two winning works, and the first place winners are Manai Han from Chelmsford County High School for Girls, who received the first place. Congratulations, Manai. And another first place goes to Tomasz Kinowski from Cats in Cambridge. Congratulations, Thomas. With that, we finish awards presentations, and we hope to see for a second the winners on our screen, so that we can wave to each other and celebrate their success all together. So if you could please switch on your camera, switch on your mics. And then we will appear. Just a few more. Right, so more fast. So yeah, members of families, teachers, please put your camera if you wish to appear on the screen on YouTube for history. So yeah, congratulations to everyone. Just see, maybe some other image can be generated. I see that there is some questions arrive from Raphael. Raphael is typing something. Right, okay, so congratulations. Thank you, well done. So we move to our second part of program, And I'm very happy to welcome the chair of Lincoln Physics Challenge, Dr. Fabien Paillusson, who will be speaker of tonight. So we'll just wait and Dr. Fabien Paillusson appear on the screen. Hello, Fabien. Your microphone is mute.
Yes, he was, yeah.
Yes, pleasure to have you here. And we had fantastic challenge. We have winners with us, and we have audience watching us. I'll tell tell again that few words about Fabien as a speaker. Fabien is a senior lecturer in our school, mathematics and physics. He received his master's and higher doctorate degree, PhD in theoretical physics from the University of Pierre Marie Curie in Paris, which is a Sorbonne university currently, and it used to be Sorbonne centuries before. He spent several research positions in several universities, such as University of Cambridge, University of Barcelona, and Durham University here in United Kingdom, before joining our school in 2015. And I'm very happy that Fabien can give us a lecture tonight on vacuum. So floor to you, Fabien.
Hello everyone, this is Fabien Paillusson here. This is a great pleasure. To give this public lecture for the University of Lincoln Science Week 2021. And what I'm going to talk about today is a very simple question. In fact, is a vacuum empty? And I want to provide here a modern physics perspective about it. And then we are going to see, whether a vacuum is empty or not, according to these perspectives. So first, we need to clarify a little bit what we mean about vacuum. So a vacuum here would be an isolated region of space. So it has to be somehow limited in space. And usually inside it, there are stuff that can be acted upon, right? So it can be a substance that is in there or anything you can imagine. Now, once you've got this, then you've got a tool or a device that enables you to suck, if you will, this substance which is inside or this stuff inside this particular region of space. So upon doing so, you will do this and you obtain a vacuum. Okay, so essentially, if I summarize this particular picture, you get that you've got things, then you remove them. Okay, so that's a vacuum. Now, what do we mean by empty? That's more of a philosophical question here. And basically, it means that there is an absence of something. Okay, so that's what empty really kind of means. Now, you've got this usual, question, which is about the glass being half full or half empty. Now, what we can say about this is that the glass may be half empty of water, right? So it's of something. So it may be empty, half empty of water. But it also actually always filled with something because there is air around it. So the actual glass is always filled, but only half of it is filled of water and the remaining half would be filled with air. So the thing here is that what is nice when we've got this idea of empty of something, we can then try to conceive a glass which would be completely empty of any matter content. Okay, so that's what at least we can conceive of. So once we've got these two definitions, what we can say is the following. If we take away all that can be removed from an isolated region of space, is there something left for physicists to talk about? Okay, so that's what I'm going to discuss today. If we take away all that can be removed from an isolated region of space, is there something left for physicists to talk about? Now, if no, then what that means in practice is that current physics may be able to address the question of a physical nothing. So if there is something, if you will, that can be removed, so that there is nothing left, if you will, for physicists to talk about, then there is somehow a conception of physical nothing. Now, if the answer to that is yes, okay, so if you take away all that can be removed, but there is still something to talk about, then what that means that current physics doesn't support the idea of an experimental situation which would be identifiable to a physical nothing, where basically there's nothing left to talk about. Okay, so that's what we are going to do today. Now, for sure, this is not an easy question to reply. So in fact, in 2012 there was a debate, so I think it's still quite recent, at least 2012, it's almost 10 years now, and that was between Lawrence Krauss and David Albert. Now, these two gentlemen are actually experts in their own right in quantum mechanics, and they strongly disagreed on basically these notions of vacuum and whether there would be something to talk about. Now, there is a strong disagreement here, and the strong disagreement between these two professionals of quantum mechanics and physics in general was about nothing and what you mean what they mean when they mean nothing. Okay, now it turns out that in this particular talk I'm going to focus not on what these two gentlemen actually disagree on, but in fact what they would agree on. So the point here is that we are trying to answer on the fact that regardless, okay, of their disagreements, we can focus on the definition of a vacuum where both of these experts would actually agree on. Okay, so that's what I'm going to look at in this particular presentation. So that's what I'm going to mean by modern physics. So I told you that it was a modern physics perspective at the beginning of the lecture, and that's what I mean by a modern physics perspective. It's basically where these two experts are going to agree on this notion of modern physics perspective. So let's start with trying to define and see how physics talks about vacuum. So first of all, let's imagine you've got a chamber which is made of, I don't know, glass or something, which is isolating a region of space, and basically it's actually filled with air or a particular substance. Okay, so the thing that you can do to find out whether it's actually filled with a substance or not is actually make sound travel through it. So you take a microphone or a megaphone or anything like this, then you send sound waves through them, and then if the actual sound waves do propagate through this particular cavity or chamber, then that means that there is a substance that enables the travel of this particular sound wave. Now, if you empty the box of this sound carrying medium, okay, so that's what I'm doing here, then upon essentially shouting at the box or sending a sound, essentially nothing is going to traverse the actual chamber, okay, and that's because the sound carrying medium has disappeared. Now, because the sound cannot propagate further, that's a way to identify the absence or the empty character of the box with regards to the sound carrying substance. Now, it turns out that this is an actual experiment which was performed by Robert Boyle and which was reported in an article of his, or treatise of his, which was New Experiments in Physico-Mechanical Touch the Spring of the Air and its Effect. And here, this is a representation. When you've got the link, if you want to get there, it's a beautiful representation of the vacuum chamber device, which was developed and used by Boyle in this instance. And he did actually prove, if you will, to his peers that he managed to obtain vacuum precisely by showing that the sound did not travel anymore through the chamber. Okay, so once we're there, then we say, well, there is something that kind of remains, right? And in fact, you can ask yourself, well, how do I know whether it's completely empty or not? So let's continue our use of waves to find this out. So if I actually use a lamp torch, then I'm going to shine light through it, and then the light is going through the actual chamber. So it's traversing through, and then I can see the actual light even if I'm across the chamber. Okay? So what that means here is that it seems that there is something left for light to travel into, which is inside the box. Okay? Otherwise, by analogy with what we have with sound, then in principle light wouldn't be able to travel. So that's where we are essentially. So now that we want to talk a bit of light, then what I'm going to do here is provide first, for the physics of propagation of light, I'm going to provide a 19th century explanation or interpretation of how light travels, and it's related to electricity and magnetism. Now, for the most part, this is how we need to this is how modern physics understand light travel. Okay, be it for antennas or optics in general, you would get something like what we are going to discuss. Now, before discussing anything here, I'm going to focus on the electrical character of light propagation, and it's just because I don't have the time here to also go on to the magnetic aspect as well. Now, you simply need to imagine that it's the same thing as what I'm going to show, but just somehow in a higher dimensional space or with a more complicated object, okay? But at the end of the day, like the basic stuff is going to be in what I'm going to present. Now, electricity here, we need to summarize, a little bit what electricity is about so that we are on the same page to move forward to understand light propagation and then, vacuum related to light. So here we imagine like a spherical object that can carry electric charge, okay? So that's represented by this dot here. And the color code that I'm going to use is that this is going to be green if there is zero charge, then this is going to be red if there is a positive charge, and then it's going to be blue if it carries a so-called negative charge. So it's as if you had three types of charge, if you will. Now, the thing is that on top of this, there is some rules to be followed. So if you have, for example, next to each other a negative charge and a positive charge, then the rule is that they are going to attract each other. Okay, so opposite charges attract each other. The second rule is that if instead of a positive charge, you put a negative charge next to a negative one, then they are going to repel each other. So the rule here is that like charges repel each other. The same would be true if you had a positive charge with a positive charge as well. So these can graphically be represented by plotting a field of arrows showing the direction of the force on a hypothetical positive charge. So this would look like this. And indeed, if you look at a case where you've got a particle a red, positively charged particle, which is at the same position relative to this blue and red particle, then you are going to observe these two different behaviors. They are following the arrows. Okay. Now the issue is that working with arrows is not that convenient. Okay. And so instead, what people try to do is to get rid of the arrows and replace it by some kind of landscape, a topographical landscape, if you will, where you've got a color code that tells you that the this landscape, the topography, if you will, the altitude is the lowest if this is blue, and this is the highest if this is red. Okay, so it's some kind of altitude. Now this altitude is not like an actual altitude. This is the altitude or the magnitude of something called the electric potential. And the rule here is that essentially positive charges always go downhill. So in this particular case, we've got a blue and a red particle, which are creating an electrical potential landscape. And essentially, if you say then that positive charges go downhill, then you are going to get the directions of the arrows. Okay, so this enables us to actually get rid of these arrows, because we just need to keep in mind that we go downhill naturally. Okay, in the same way, to be honest, that if you drop a ball on a hill, it's going to go downhill. So it's more intuitive, if you will. Now, of course, having these arrows superimposed with this particular color code is not really easy to visualize. So instead, what we can try to do is start with basically with a three-dimensional representation. So now what I'm going to do is that on the left, I'm going to put at the central part, I'm going to put a negative particle, and on the right, I'm going to put a positive particle. And we are going to see how it's affecting the landscape of this electric potential. So I'm going to charge the actual particle, and as I do so, it's equally deforming the actual landscape, okay, this electrical potential landscape. Right, so this is how a particle is going to affect the landscape of the electrical potential landscape, and the rule here is that, again, you go downhill, or positive charges go downhill. So what that means is that essentially that would look like this. Red positive charges are repelled and they go downhill from a positive charge, and on the contrary, they are attracted downhill by a negative charge. Okay, so now let's have a look at something a bit different. Now I take again a positive and a negative charge, and I'm considering this as being the two ends of a capacitor, if you will, or some kind of antenna. So if I actually look at it, then I've got alternating current, and what this is going to do is alternate and change the polarity of this circuit. Okay, so that's what this is I'm going to look at. So far I'm not visualizing the actual electrostatic potential, but now we are going to visualize it. So if I actually put and look at the actual potential, that's what it looks like. Okay, so it actually changes with time, and it goes up and down on the different locations of these two charges. Okay, so that's what an electrical potential looks like when you are at an alternating circuit, at the two ends of an alternating circuit. Okay, but from this, to be honest, we can't see very much, and it's not clear how this relates to anything we've been talking about so far, especially with vacuum and light propagation. Well, it turns out that if you zoom out a little bit, then this is what you're going to observe. So here I've zoomed out and removed, for convenience, the the apparatus, the generator, and the two charges. But what you see here is like the positive charge, and here's the negative one. And what this looks like is like this. So this is simply zooming out. So you see here that what's going on is there are ripples which are going away from the center oscillating location, and that's it. So we've got ripples that are propagating on the electric potential. So this particular description is what we call electromagnetic waves. And this is the most current, or at least classical explanation of light. Light is electromagnetic waves. Okay, so when I'm looking at this, I'm actually looking at light. So once we are there, then we can ask ourselves the following. So light then is understood as ripples in a potential field. Okay, so that's basically the best 19th century description of light. But at the same time, does that mean that light propagates in a medium? Okay, so I don't know if you see what I mean. Does that mean that it propagates in a medium? And the question, sorry, the answer to that is kind of sort of, but the medium is not made of matter. Okay, so it's as if it was its own medium somehow. And so the point here is, can we get to remove this potential from a region of space? So I told you that you've got these ripples of the electrostatic potential, and then we want to know whether, well, basically this kind of potential itself can be removed from a region of space. Now, the current understanding of these ideas is that actually no, this potential, this electric potential, permeates the whole of space at all times. Okay, so that's where we are so far with this 19th century interpretation, if you will, or classical interpretation. Now, the thing here is that there are two main issues with this view, which we need to address in order to have maybe a better picture of a vacuum related to light. So the thing here is that when you look at, there are historically two issues that were with this particular picture, classical picture. So there is a difficulty to explain consistently, if you will, the glow emitted by heated material. So here, this is a snapshot from a forging video on YouTube, and where you see clearly that there is, a shine emitted by material which is being heated. Okay, so you see, well, aside from being beautiful, you see that there is a definite glow to it, and that's related to temperature, and so there was a big problem with this. Now, there is a second problem, which is that of the so-called photoelectric effect. So here, I'm simply showing an application which can be used for free on the internet, and I've put the link at the end of the lecture. So there was a phenomenon which is as follows. So here you've got a lamp, and here you've got basically a setup with an anode and a cathode. And what happens here is that you can change the intensity of the light, okay? So as you increase the intensity of the light, then basically nothing happens if you are in the very large wavelength, so low energy light. And there is a slight potential difference between anode and cathode. And then eventually what happens is that you obtain a current that flows. So you obtain electrons which are being ejected from one of the plates and then going onto the other one. Interestingly, without changing the voltage, okay, you can get an increase in the current that is being released simply by changing the frequency of the light. Okay, so this is called the photoelectric effect. Now it turns out that to solve these particular two puzzles, for the one having to do with the glow of a heated metal and that of the photoelectric effect, then what had to be obtained was to use the idea that light was made of particles, or so-called quantas. So the glowing problem, assuming quantas, was solved by Max Planck in 1901, and then the photoelectric problem was solved by using quantas again by Albert Einstein in 1905. In fact, that's what that's what he got the Nobel Prize for in physics. So So the thing here is that the modern view combines somehow the idea of the field picture I've shown earlier. We've got these ripples on the potential and the particle quanta concept from Einstein and Planck. And the way it works is as follows. You've got potential fields, exactly as I've discussed earlier, okay? But then particles of light then are expressed or interpreted as being elementary excitations of that field. Okay, so what that means by elementary is that you cannot have anything kind of smaller than this in terms of amplitude and energy. That's kind of what it means. And these particles of light, which are elementary excitations of this field, are what are called photons. At least that's what they are called now, photons. So on top of this, you've got that all of it is expressed in something called quantum mechanics. Okay, so I'm not going to enter into any details whatsoever on quantum mechanics. This is it would take a whole public lecture or more. But what I want you to at least take on board is that quantum mechanics is inherently a probabilistic theory. Okay, and so what that means is that numbers are never definite. They have this opportunity to change, if you will, in time, or at least upon repeating measurements. So here we've got vacuum 1.0 was you've got a particular vacuum of where that you've emptied of matter, and then you've got no particle of it once you've emptied of it of matter. And then you basically the state of the light itself is kind of undetermined. Okay, you've got simply light that goes through it, but that's it. You can't really address or talk about empty this region of space of light. Okay, so here we can try to have a new definition of vacuum where we would have like a 2.0, for example, where we have indeed no particle of matter, but then we also have no particle of light, okay? And so if we have no particle of matter and no particle of light, it means that there is a form of excitations which are not there, okay, which are the minimum ones that can exist in terms of so-called excitations. But at the same time, we need to keep in mind that the whole thing is probabilistic. So what that means in practice is that although on average you're going to have a flat potential, electric potential, is going to fluctuate the potential itself about this zero value. And this is actually going to look like this. So that's, in my opinion, one of the best kind of visualization that I could provide on this. So that's what a quantum vacuum would look like in a cavity where you somehow are able to isolate this particular vacuum. Okay, so these things would be a representation of this vacuum 2.0 or a quantum vacuum. Now, once we have seen this, does this ever bubbling vacuum appear empty to anyone here watching this video? Well, it turns out that maybe not, right? If you see this thing kind of moving around, etc., it doesn't seem that empty. But you could also say, and rightly so, or legitimately so, that it could also be a mathematical artifact where this bubbling basically occurring in this vacuum has no effect on experimental data. And then that would be more like a philosophical concern whether this is actually real or not. So to address this particular issue, what we can do is try to look at what is the definition of a vacuum if we go back to the, some of the founding fathers of this idea. So here I'm going back not too far, but to Newton. And what he says here, I'm not going to try pronounce it in Latin, but it's like vacuum. I call every place in which a body is able to move without resistance. Okay, so that's the definition, according to Isaac Newton, of what a vacuum is. And what that means here is that there is essentially you can probe whether you've got a vacuum or not through basically its mechanical impact on motion. So the problem here is that there are experimental evidence that there is such a thing as quantum vacuum friction. And here I'm just highlighting one of the parts, is that the quantum vacuum, you see in the abstract, may in certain circumstances be regarded as a type of fluid medium or ether exhibiting energy density, pressure, stress, and friction. So by Newton's definition, then the vacuum I'm talking about, so the vacuum 2.0, does actually even provide friction and then resistance to motion for certain objects. So that's the first aspect of it. Now, here, this is another one here that there is on top of it. This is a paper from 2011, that observation of the dynamical Casimir effect in a superconducting circuit. So that's basically an experimental evidence of what was before a theoretical claim that this could lead to friction, pressure, and all that. So this is an experimental here, evidence of this. So it seems to be actually, more complicated than it looks, isn't it? And there is a further case as well. So you see that there is cases where you've got a pressure difference in air, and that can have devastating or very dramatic effects on objects. So for example, here, this is a very well-known case. You've got a tank, and the tank is actually being emptied, or is actually empty of its air content, and is simply crushed under the atmospheric pressure. Now, it turns out that there is a similar effect which is being predicted in a vacuum. Okay, so in the quantum vacuum 2.0, there is this kind of pressure effect being expected. So this is what is called the Casimir effect. Here you are represented two plates, so it's a side view. You've got two metallic plates that are there, and it turns out that the vacuum pressure is supposed to be larger from the outside than from within, okay, this particular slab. And so this pressure is caused by the bubbling, if you will. And so the bubbling is supposed to be larger or more, with more magnitude outside of the plates than inside, and as a result you get a higher pressure. Now again, here this is just one of the many papers that have been published on this particular topic, where there is a measurement of the Casimir forces between basically some structures, some matter content. So again, here there is vacuum between them. These things are obviously not charged, so they are not like attracted or repulsed by simply being charged. It seems to be interpretable as due to the vacuum pressure. So from these things, what we can say as in terms of closing comments is that quantum vacuum, as far as we know, is the most empty state we can theorize in our current contemporary physics, and where the two gents I presented initially would agree on. Okay. Now, there are conceptual expectations. It fails, to meet conceptual expectations, so that it's basically empty. And in fact, we've seen it with some kind of bubbling substance or stuff that is bubbling, even in the best case of emptiness, if you will. We've seen as well that there is phenomenological expectations of an empty region of space, which are not met by this quantum vacuum, because experimentally speaking, there is both resistance and pressure being exerted by the best vacuum we can think of. Okay, so as a result, with regards to our initial question, if we take away all that can be removed from an isolated region of space, is there something left for physicists to talk about? Well, the answer here seems to be yes, or at least is leaning to a yes. Now, does that mean that this is the end of discussing kind of emptiness or anything like this? Well, it turns out that depending on the traditions and culture you look at, empty means something very different. So, for example, in Buddhist traditions, which is of course quite far away, this to some, from quantum mechanics, empty means something very, very different, where instead as, let's say, put forward by Friedrich Capra in his book, quite at least popular book, The Tao of Physics, where he makes links between quantum mechanics, for example, and Buddhist tradition, then he actually says, well, look at the current definitions. In the sutra says form is emptiness and emptiness is form. The quantum vacuum is truly a living void, pulsating in endless rhythms of creation and destruction. And that's the kind of things that emptiness means in Buddhist traditions. So I leave you with this. I do not know whether obviously this is the end word about it, but hopefully this will make you think about it and maybe read more on it. So I thank you very much for your attention. And if you want to have a look at the actual content where some of these images or articles have been taken from, then here are for the images, and this, so that's still for the images, and this is for further reading if you want to. Right, so I hope you have enjoyed this lecture, and I hope you're going to enjoy the rest of the lectures we will provide with the University of Lincoln.
Thank you very much, Fabien, for your fantastic talk. And I'll just ask you to come back to the virtual space.
Yes, I'm back.
And then we can discuss this talk, and the questions can arrive using several channels. First of all, people can put in a live chat in YouTube. They can put in a Padlet link, and in fact some people did it as the talk was happening. And winners of Lincoln Physics Challenge who present together with us in this virtual room, they can also ask questions directly in the chat of this virtual room where we are. So let's before we maybe go to questions, I'll read one of the comments, which is from Viv Forbes. Thank you so much for these wonderful lectures. I haven't seen them all, but I'm not a physicist or mathematician, but I have learned something from everyone. Thank you very much, Viv. And then we look on the question in the Padlet. And then the first question is, how would you determine that the sound has indeed traveled through the chamber, through the inside of the chamber, and not just through the walls of the chamber?
Well, I suppose the idea is, I mean, one way to appreciate this is precisely by doing Boyle's experiment. So you could assume, and in fact it probably does travel on the walls of the chamber, but when it travels inside the material, inside a much more solid material, then it requires air inside to actually resonate, etc. Exactly like for a guitar or things like this. If this is not there, then there is something called acoustic impedance, which theoretically speaking will probably give rise to almost no travel of sound through the chamber. So that's theoretically speaking. Now let's assume you say the sound is going to travel only through the walls of the cavity, and then it's going to propagate to some listener away from the cavity, and opposite to you when you're shouting or whatever. Then you can test this hypothesis by creating a vacuum in the chamber and see whether the person is still listening to you. In fact, you may have, at least some time ago, when I was going to supermarket, or at least this hypermarket where you would have music to listen to, you would buy CDs. If you remember, you had at some point some glass bells on top of your head so that you could listen to the music. And in fact, if you were next to somebody like this, you would see you couldn't listen, you couldn't hear the music. So the glass bell was enough to actually block the sound. And obviously, you were not put in a vacuum bubble, otherwise you would die. So so it seems that at least a glass bell is enough, right, to just prevent the sound to propagate. So the idea here is that there are multiple ways. I think Boyle's experiment actually proves, in some sense, or is evidence that sound needs somehow like some kind of medium to travel through. And if somebody would not be convinced by this, then they would need to propose maybe a different manner of determining whether they did obtain a vacuum or not. And so I think a way to do that would be with a cavity, which, by the manipulation of a switch, for example, would become soft. So if it becomes soft, then it will collapse under the pressure, and then you can tell, okay, that's how actually it works. So I did create a vacuum, and apparently that seems to correlate with the absence of sound traveling through the chamber. So at least that's one way you could do it. I think.
Thank you very much, Fabien. I just mentioned that this final lecture lasts slightly longer as it was advertised, as it is also combined with award ceremony. So we have a little bit longer time. And I see there is a question arrived from Sue Flower. Welcome. Do you think we will be ever able to create a complete vacuum with absolutely nothing in it?
Well, I mean, that's kind of the point of the lecture, right? So the thing is that as far as I can say, and as far as I understand, we can't do better than a quantum vacuum. And a quantum vacuum still has something in it, right? So it still has something for us to debate and talk about. Somehow it exerts pressure on the actual confining wall. So that's kind of the always a tricky bit with vacuum, is that because you need to isolate a region of space, then you need to have actual material walls which are surrounding this vacuum. And in fact, that these material walls, we probe the properties of vacuum through the way they behave themselves, right? Whether they tend to compactify each other, or maybe they get repelled from each other, etc. So my take on this is that the best vacuum we can provide is this quantum vacuum, so far at least. It's always filled with this boiling field, and this boiling field seems to be real, right? And then as such, then I think that we can't really provide like a true, like, where there is nothing in there. So that's what I would say, following from what I said in the lectures.
Thank you, Fabien. There is now a question which is kind of rather fundamental and maybe partly philosophical. What does it mean for the limits of the universe? Would this imply that there cannot be nothing, as if it would not have physical properties like volume?
So I'm not sure I get the answer to the question, but one of the things is that one of the models that is being used when talking about the universe as a whole is precisely to talk about the universe that is somehow isolating, definitely not vacuum, because we're here at least, so it doesn't seem that we are made of vacuum. But basically encapsulating a region of space with stuff in there. And there is this idea that there is something that you may have heard of, which is called termed or flagged as dark energy, which was responsible for the universe to not only expand, but to also have an accelerated expansion, as far as some measurements from the 90s suggest. And the thing is that people then say that the vacuum and the quantum vacuum fluctuations, aside from us, right? We are not again vacuum, but the quantum vacuum fluctuations inside the universe would actually repel some kind of soft boundaries of the universe, and they would be responsible, in fact, for the expansion of the universe. Now, so that's one of the ways people try to estimate the so-called cosmological constant to explain this kind of dark energy thing. Now, this is a very let's say, not presumptuous idea, but this is very speculative, and the reason why it is because when people calculated the pressure that would make the from quantum vacuum and quantum vacuum fluctuations that would give rise to this expansion of the universe, they actually got a theoretical estimate which is 200 orders of magnitude larger than what is measured. So what that means is that, okay, maybe this is what is responsible for the expansion of the universe, but at least we are kind of we are falling short of getting anything close to what is really measured, and people are puzzled as to why this is so far away from it. So at least that's the closest thing I could say with regards to these questions about universe and so on.
Thank you, Fabien. There is a question arrived from Santiago, who is with us in a virtual studio, one of the winners of challenge. Where does this idea of quantum vacuum come from? In other words, how do you know it's the best we can get?
So that comes from the theoretical description. So because people started to have this quanta idea that seemed to be and still seem to be necessary to explain both the like the glow emitted by bodies with, in fact, any temperature, or the photoelectric effect, then that's the natural conclusion, is that then you can create a further vacuum by removing by having zero quanta in your system. So it's a theoretical, if you will, conclusion. You know, if you follow the idea that there are quantas of light, then you can imagine and conceive a world where there is no such quantas. And it turns out that this is something which is now casually done in experiments, where people have cavities and they can put 0 photons in there. So the zero photon, 0 atom, nothing, and then they can one at a time put 1 photon, 2 photons, and they can even like switch which modes of photons they want in there, etc. So this is something which is being done now since probably easily 20 years at least. Maybe I would say even 30, because so it came from a theoretical perspective. If we embrace this idea of quantas, then there has to exist a further vacuum than the one we could conceive beforehand, and it seems to be possible experimentally nowadays.
Thank you, Fabien. Now I see there is a question in live chat from Chris Dennison. What was the most surprising thing you discovered on your journey through this topic?
That the word photon actually arrived quite late. And in fact, so this is to be checked, to be honest, but I actually found an article, and it seems that the word photon initially was part of biology. So it was used a lot by people in biology and physiology, and that was to relate to the exchange between light and the cones and all these different organs on the retina. So photon had to do with this particular exchange for like the physiological process going on, and that would give rise to this on and off kind of switches inside the body. And then and so there was some time where it was mixed of quantas and then photons, but photons were used for different reasons. And it seems that there has been some time on history, I'm not sure exactly when, where basically people switched from quantas to photons to express the fact that light itself was being quantized. So at least that's something, when I read about it, again, that's an article you can find on the archive. I can't, probably I have actually put it in the references at the end. And at least you can check, you know, there are references in this article, so you can, you know, check for yourself and maybe have some critical thought about it. But I was actually surprised by that. There are other things, of course, but that's the one I was surprised about.
Thank you, Fabien. I see there is question actually on photons in Padlet. How do photons move in vacuum 2.0?
So in vacuum 2.0, there is no photon. They don't move. They don't do anything. I must say that what I described here is a quantum vacuum. So again, inside a cavity, and in fact, we kind of don't know how to express a vacuum if there is no kind of some cavity or specific so-called boundary conditions. Now, photons themselves, the nature of a photon is going to depend on the external and outer or border or like constraints. So, for example, a photon inside a cavity is not the same as a photon propagating in empty space, like in outer space, for example. So they are not the same. They are not of the same nature. They won't look like the same if you were to draw them, if you will. And so that's something usually that people have difficulties, and that includes myself, to represent, is that cavity photons are some kind of bubbles that are a bit like more like organized, so like some kind of music of bubbling. But then photons that propagate in only one direction, then they look different, and I'm not even sure that it's possible to visualize them in the way I've tried to visualize, let's say, the quantum vacuum. So basically, it's not I don't want to use the word should, but it seems to be unwise to visualize, to imagine that a photon is only one object. There are different photons depending on the experimental setting that you are operating with.
Okay, thank you, Fabien. I see that we approach in our scheduled time, but maybe still a little bit. There is something here, a question, are Casimir forces exist only between planes?
No, no. So they exist. So the initial plate one, so plate thing was just because it's in some sense easier to evaluate. And roughly speaking, that would be what you would observe between, like let's say, the two plates of a capacitor. So that's why also it was interesting to look at. Now, of course, any geometry. So, for example, I have worked myself on Casimir forces, and you can have between a cylinder and a sphere, or between any kind of geometries. There are also specific effects that arise due to having kind of edges, I mean, like points and things like this, which give rise to some things kind of crazy. Now, one thing I want to emphasize about this is that Casimir effect is somehow sensitive to what is called topology. So if you've got two plates and you've got a slab, then the topology is that you're separating the middle slab from the rest of the outer part of the slab. So that's the topology basically of a slab. That's a 2D kind of version of it. Now, if you've got a sphere, then you simply have one definition of inside. It's inside the sphere or outside of it. And the thing here is, if you look at the Casimir effect that occurs within a sphere, so if you take a spherical cavity, then you're going to find that the Casimir effect actually makes the sphere expand instead of collapse. And that's why people thought that could explain expansion of the universe. So this is, there are plenty of subtleties. The reason why for spheres it expands instead of contracting is due to so-called TE modes and TM modes that exist in spherical cavities, but not necessarily between plates. So, and also they would exist as well in like cubic cavities as well. But anyway, so yeah, it's possible to calculate these things for many different objects.
Thank you very much, Fabien. I see that Santiago is typing another question, but before question arises, maybe you can answer briefly. Why did you choose theoretical physics to study? This question in Padlet.
Why did I? Well, I don't know. I was interested in physics. Of course, I wanted to understand the world. And yeah, I guess that's just that. I wanted to understand the world, and when I was studying, it seemed to me that theoretical physics was the way to do it. So that's it. Yeah, I just had these things where I wanted to understand the world. So initially, I actually um, um, targeted more so-called high energy theoretical physics, so particle physics and astrophysics and things like this. But it turns out that as I actually went through my studies, I got much more interested, in fact, into a different topic, which, in fact, I had never heard about, which is called statistical mechanics. Well, some people, I don't know if some students are in the chat or on YouTube, so maybe they won't agree with me. But this is a topic which I enjoyed very much. We talk about spaces which have like billions of dimensions, and then we need to calculate volumes in there, and this has actually impact on how the physics of the systems behave, etc. So anyway, so then I redirected to different branches of theoretical physics, which have more to do with how do you relate the world you see on Earth with the theoretical physics of high energy and stuff like this. Anyway, so that's kind of.
Right. Okay. Thank you, Fabien. There is a quite technical question, in fact, from Santiago again, from in our studio. How do you define a pressure at the boundary, like the Casimir pressure, in terms of quantum mechanics?
Yes. So okay. So luckily, it's not too difficult. So the reason why it's not too difficult is because yeah, there is something in electromagnetic theory. There is something called the electromagnetic pressure. So you can associate a so-called pressure tensor, which is related to the electromagnetic field, and so at a plate. Essentially, the actual equation for that pressure at the surface of a plate is proportional to the magnitude of the electric field squared, and then there is some prefactor like 1/2 epsilon 0 if you're in vacuum, and that's it. It's basically E squared over 2 epsilon 0, and that's if you have an electric field next to a plate. Now, when you are in a quantum vacuum, what happens is that the quantum average of the electric field is actually 0. But luckily, the average of the square magnitude of the electric field is actually not 0, because you've got fluctuations. And so because of that, you get an actual pressure, which is due simply to these fluctuations. So basically that's it. It's not that's for the same reason that if you leave an atom in an excited state, then it's going to behave as if there was an electric field, even if it's been vacuum, because there is these fluctuations going on. So yeah.
Thank you very much, Fabien. And with that, we exhausted our time of this special double event of last lecture of Lincoln Math and Physics Week 2021, and also our Lincoln Physics Challenge award ceremony. I would like to thank Fabien for wonderful lecture, for preparing and chairing such a challenging physics challenge, just a bit of the double wording. And I'd like to thank participants of Challenge, who some of them are here with us in our virtual studio. I'd like to thank everyone who watching us virtually on YouTube for all your questions as well as comments. As always with our lectures, we've got more questions in Padlet when there is time to answer. But thank you very much, everyone, for attention. And I'll just see from Andy Ellison, last comment, excellent series of lecture. I hope you continue even after the pandemic. Yes, we will continue. Thank you very much, everyone, and goodbye.
Thank you very much.